Okay, so questions. Design assignment, anyone? Well, if you don't ask questions, that's the surest way of not being able to do it. So, okay, so I'm assuming that you're all good to go. One thing I would like to emphasize, a few things. Okay, so firstly, um, you are not allowed to modify the top level file. Okay, so we are going to take your modules called MCTX and MCRX and going to plug in into a pristine copy of the top level design. So do not mess with wiring of the keyboard and stuff like that. Those, for example, you are not allowed to replace the clock signal of the keyboard and things like that. Those are not allowed. So you should not mess with the top level design. Okay, so that's very important. Just design the MCTX, MCRX, and any other sub circuits that you need. Keep creating them in the same file. There should not be any other .circ file. Okay, so everything just goes in there. Just create those two designs. Do not change the top level design. So that's point number one. Point number two, some of you came to my office hours, you are approaching it using data paths, and that's perfectly fine. If you are using a data path oriented approach, in that case, you should provide the kind of pseudocode we were using in the previous two lectures for the output function and the next state function. So instead of an FSM diagram, you're going to provide that pseudocode function. Or if you have a design which has a data path and an FSM, then for FSM, either give me a FSM file or give me a hand-drawn state diagram or whatever state diagram drawn some way, and for the data path part, give again that pseudocode. So your design can range from entirely FSM to entirely data path or something in between. There was also, so any questions on these 2 points firstly? Okay. If you have not started this homework, I strongly urge you that that's the first thing you should do right after this class, because you're already probably too late to kind of do it. So it's not an easy design assignment. I handed it out a week and a half ago, so it's been plenty of time. Do not delay it. I do not give the homeworks with the intent that you will approach it in the last 24 hours before the deadline. Okay, that just doesn't work. Okay, so some additional points. So just guidance in kind of potentially approaching this problem. So insert blank page. Okay. One point which came up is this relationship between clock cycles and timing on the Morse code. Okay, so essentially what is happening is that you have these two blocks, MCTX and MCRX, and they're talking using a single wire. On this wire, we are sending out Morse code.
But was there a cost to specific units, or so we're like, does each gate cost a specific amount of money, or can they?
In this assignment, you can use any module, and there's no consideration of cost. Okay. Which is why those of you who did not have a functional design homework 2, if you want to use it, you just create it using ROM. It's just a table. We are not going to provide that. Okay. So anyway, on that wire, we are seeing the dots and the dashes going out, and Morse code has its own timing. Morse code says that imagine there is some time unit, and a dot is equal to a value of 1 for one time unit, du. A dash is equal to 1, 1, 1, where each one is that one time unit, and likewise gap between letter is a single 0, so value of 0 for one time unit, and so on and so forth. What this one time unit is, so 1 Morse time unit is going to be some n clock cycles at the transmitter, and that n is your choice. It could be 1, and certainly possible to do the design with n equal to 1, which basically means that whenever you are sending out a dot, that means for one clock cycle, the wire would have a high value, and then whenever you are sending out a space between a Morse symbol, then it would be a 0 for one clock cycle, and so on and so forth. But if it turns out that your FSM is sluggish or your data path is sluggish, then maybe n may have a higher value. That's left up to you. In the design assignment, I also say that transmitter and receiver have the same clock frequency, but the edges may not be aligned. Okay, so it's possible that this guy's clock looks like this, and so that may be this guy's clock, and this guy's clock may look something like this. Okay, and in fact, the setting of the clock, the way it is in the assignment, it is kind of like that. The edges do not come at the same time, and your design should still work. So I want you to think about the receiver and the transmitter separately. Do not make an assumption that they are on a common clock, other than that they have the same frequency. Okay, so that's the second point. Third point, as I said, you can approach designing these things, as we saw, and entirely using FSM, entirely using data path or some combination thereof. Now in design homework 2, you already did the module which takes ASCII code to Morse code and Morse code to ASCII code, and we had a particular encoding for the Morse code. In the Morse code, we basically said that we are going to think of the Morse code as 5 symbols, because the maximum number of symbols that a Morse code encoding has is 5. 5 dashes or 5 dots or some combination, which is for the numbers. So 5 2-bit symbols were sufficient for the Morse code, and the ASCII code is 7 bits. So what's happening is I have a keyboard. That's our keyboard. Here we have ASCII. Okay, and it is coming out parallel. I'm getting all the 7 bits in one go. Okay, so this is 7 bits. And then here I have a display, and that also takes ASCII, and that's also 7-bit. And additionally, the keyboard has some handshake signals. So the keyboard gives out the user types into the keyboard gives out the oldest character in the buffer into the output with that ASCII output, and it does so only when there is a clock tick and the enable signal says hi or is asserted. And then it pops out that character which you are supposed to read it, and then next time there is a similar clock tick, that is a clock tick with the enable signal hi, then the next character comes in. So there's a handshaking going on. So the idea is, if you don't want to read from the keyboard, don't do the enable signal. If you want to read from the keyboard, do the enable signal. The keyboard will present the character, and then it will pop it out from the buffer. So the thought I had, one way you could approach this thing is that the MCTX, you can think of there as a state machine, which on one hand is talking with the keyboard, it's handshaking with the keyboard, and on the other hand is handshaking with an adaptation of your design homework number 2, which basically now takes the ASCII character and spits out the 10 bits as 10 bits of Morse code, 5 symbols of 2-bit each. And then those symbols have to be sent out serially over this guy. So that could be done by yet another state machine or through some sort of a shift register. So you can think of the MCTX as kind of the 2 sides to it. There is one side which is a stage which is doing the actual coding, and the other side which is the interaction with the keyboard. So you get a character from the keyboard, hand it to the coding stage, and when the coding stage is done, it gives you a done signal. You get the next character, kind of do it. You'll have to do a little bit of overlap, but it's a little bit along the lines of the vending machine that we saw, where we had the drink dispenser and the change dispenser, and they were sending us a done signal. So you can wrap your combination circuit from design homework 2 or just design using ROM along with some shift registers or some other registers to kind of make this this module to which I hand an ASCII character and say go. It encodes it and sends it out over the wire. And then when it is done or close to getting done, it sends you a done signal, and at that stage you feed it the next character from the keyboard. And keyboard is infinitely fast because you, in the sense that you can keep getting a new character every clock tick. So your bottleneck is actually sending things out. The shortest character is going to be a single dot. So I don't know which letter it corresponds to, but a single dot will take 1 clock cycle of high and then there is always a inter letter spacing, which is going to be 3 zeros. So 4 clock cycles would be needed at least to transmit the shortest possible Morse code character, and that is assuming n equal to 1. That is, my dot is equal to a single clock cycle. So you have plenty of time. That is, your coding stage has takes 4 clock cycles at least to send that character out. So that means you have to go back to the keyboard only no sooner than the 4 clock cycle. Okay, and of course, in general, a lot slower. It's hand raised out there.
So how optimized is this circuit required to be in that, like, could you say you have 10 clock cycles for your each bit is 10 clock cycles. So say you would have your basically say you would assume worst case for both sides. Would that be okay? Or
I don't know what you mean by that, but if I gave you, let's say, the word hello, HELLO, then between H and E and L, the spacing should be exactly the spacing between two letters, which is three Morse zeros. Okay, so three n clock cycles of zeros. Okay, anything more will violate the intent. Okay, now I'll come to you just a second. Okay, but between two bursts, so let's say I did hello, send, then I waited, then I say how are you, send, then between the O of the hello and H of the following phrase, there would be a long period of time, and during that time you just transmit zeros. You can think of it as you're transmitting a space which is which just is worth many clock cycles. Okay, but the hello should go out observing all the time, so you cannot insert arbitrary amount of spacing between H and E. Okay, because that will violate the Morse code requirement. Okay. Okay. Now there was a question first to back.
Why would it not take at least 4 clock cycles?
Because between two letters there is a spacing of 3 time units of zeros. So let's say the character for corresponding to dot was X. Okay, I don't know what it is. Okay, so let's say it was X, but following X there has to be something. Okay, whatever it is, there will always be some spacing. Okay, so that's all I meant. Okay.
So does that mean that every clock tick there will be a new 7-bit input?
No, it's up to you. Every clock tick there can be a 7-bit input, but keyboard is handshake driven. You tell it when you need a right? And clearly, if there was a new input every clock tick, the system is not workable, right? I mean, I can keep feeding you characters, and since Morse code takes multiple clock cycles, as we just realized that even the shortest character will take at least 4 clock cycles, okay, accounting for the inter-letter spacing, so obviously cannot be. So that was the whole thing I was saying earlier on, that there is a signal on the keyboard which lets you say, now give me the next character, pop the next character, pop the next character. Okay, so it's under your control. Okay, and what you would see in the top level design is that the signal, I think it's called, anyone remembers what that signal is called? Do you remember? The one which lets me pop a new character from read enable. Okay, so the read enable signal basically is the one which basically says when read enable is high and a clock tick comes, then the keyboard pops the frontmost character from the buffer. And if there was no character in the buffer, I think it outputs a 0. Okay, and it also has a signal called available or something like that to indicate that there was indeed a character there.
Are both your keyboard and your transmitter on the same rising edge clock?
Yes. And that's obvious from the top level design, right? I mean, we are feeding you the same clock. If you look at the design, there's a clock sitting at the top and it's going to the keyboard and it's going to your module. And likewise on the receiver side, the clock going to the display and the clock going to your receive module is the same. The clock going to the two sides are different. Okay, and in particular, they're the same frequency, but their edges may not be coming at the same time. Any other questions on this one?
So when you were talking about like Verilog and Prism, can you just like do the whole thing in Prism, export it to Verilog and plug that into Logisim?
You could. One thing I'm realizing is that remember there's that manual stage where you have to take the output of Verilog and then enter it in Logisim, and I think students are finding that hard. Okay, because it's a very messy looking netlist. My suggestion is that the way to combat this issue is the following: keep the part which should go into FISM should be state machines only. Do not use it for data paths, and do not use for things lots of states. So the example I was giving, that I have a simple state machine which is taking data from the keyboard and giving it to the next stage. That state machine should probably have, I don't know, 3 or 4 states, no more, and that FISM is perfectly fine. But if you have state machines with 10, 12 states, guess what? The logic which will come out of it would be insanely complicated, and then and once you start getting into that, that probably means that you should rethink your strategy at that stage. Okay. The other thing I would say is, before diving into circuits and gates, first think about how would you address this problem if all you were doing was writing a program. Let's imagine that you were writing code and this MCTX and MCRX were running on some infinitely fast processor, and you were writing a program which is monitoring these lines from the keyboard, controlling lines to the keyboard, and setting these lines which are that serial line. How would you approach that? Okay, first think about the algorithm that you're going to follow, the strategy that you will have, before diving into gates and all, because the focus of this problem is getting your architecture right. Okay, the combinational part is trivial out here, right? Because I'm letting you use ROM, so you can just write your truth table into the ROM and you're done. Okay, so it's really, the focus is on getting the sequencing of the operation right, and doing the FSM and doing the data path if you need to.
Can you guarantee that the input to the keyboard, or like the longest word, will be less than 32? Because like the keyboard only takes 32 characters.
Then and therefore it's automatically guaranteed, right? Okay. Yeah. But you shouldn't need to do any buffering, extensive buffering within that module, because you can always get the next character on demand from the keyboard. So the idea is you fetch the next one, and as soon as the current one is finished, that is, your coder tells you I'm done, you give this, hand it over to the next stage, and meanwhile you have at least another 3 clock cycle, 4 minus 1, at least that much to fetch the next character. Okay, and if you start running into trouble there, just increase n, just make it slower. That is, make your dot to be worth more clock cycles, and that will just increase the Morse code transmission time. Receive side, again, one way of thinking about this thing is I'm getting these things, and look for certain patterns. So a dot is going to be, assuming n equal to 1, that is, a dot is a single clock cycle, then a dot is nothing but the pattern 0, 1, 0, and a dash is the pattern 0, 1, 1, 1, 0. Okay, anytime I say this, I have a dash, and okay, so I can put some sort of a pattern matcher out there, and then anytime I see that, I can translate that into the kind of coding we were using for dot and dash in design homework 2, where dot was 0, 0, dash was 1, 1, and if I recall right, I think it was that, right? And then you can feed these things into a shift register of some form, and then use your design homework 2 logic to decode that. So make use of these different modules. Think a little bit along data path lines, and that might be useful also. And again, if you think in terms of pseudocode, that's what will pop out. Any more questions? Okay. So next topic that we are moving to is something that some of you are anyway discovering, which is we can use ROMs and state machine. And that ROMs and state machine is what is called as microcode based design. So let's talk about it. So sequential system, as we saw, they all essentially at the end of the day look like I have some state register and I have some combinational logic, and the combinational logic implements output and next state. Whether we come at it through FSM, state transition diagram and all, or whether we come at it from a data path perspective, eventually this is what I have. I have next state and output, and I have the state diagram. And we saw 2 ways of implementing next state and output thus far. One was we use our Karnaugh map type approaches. So that's how we did originally with FSM state diagrams and work of that. And then when we came to data path, these things were done using multiplexers and adders and stuff like that. Okay, so that's, and also some arbitrary combination logic. There's a third way in which, going back some lectures ago, we saw that any combinational logic can be implemented using a ROM. So what if we were to replace all of this thing by a ROM, and then it takes my current state and external input and produces the output and the next state. So the idea is, let's, instead of worrying about gates and multiplexers and all, what if I use the ROM? Now, again, this strategy will not be very efficient for data paths, because data paths have many bits, so n is very large, so ROM would be huge. But for our standard state machines, where we were using the state diagram and all, that this could be a perfectly fine strategy. So for the control FSM, that's a perfectly fine strategy. So basic idea then is, through the ROM, I have this general purpose combinational circuit which takes n bits and produces d bits. It can implement any function which has n bits of input and has b bits of output. So conceptually, ROM is a table where I have 2 to the power n slots, and each slot holds a constant value of b of b bits. And then whenever I want to find output, I just feed it in, it goes, looks up into that slot, and whatever is the constant content, it puts it out on the output. So I can, the ROM content kind of look like the truth table. We saw this earlier. So what if we can, what are the ramifications of implementing this next state and output using the using the ROM? And that actually is the concept which was realized very early on, and in fact it's one of the first emergence of kind of a general purpose computer. So sort of the idea, so there was this gentleman called Wiles in UK. What he did was, he basically said, let's put our state transition table, the one which encodes the next state and the output, into a ROM or a RAM. And the idea is that we use the current state and the input as the address to this ROM, and then this ROM will return us a value, and that value will tell us the next state and the outputs that are going out. So that's what's going to happen. And now what we begin to do is, we basically begin to think of this thing as kind of a little bit like a program. The address is where the instruction is stored, and the content of the ROM is the instruction, and they call it micro instruction, and we'll see why shortly. So essentially, the content of this ROM could be thought of as a little bit like a program, and we'll see that how we can actually make it look very much like a like code. And if any of you have done some of the CS33 or something like that, you may have seen microcode already, perhaps, but this kind of is exactly the same thing. So this is what's happening. Our sequential system we have now replaced by a state register, and here, what for the moment, ignore this bottom register. Just imagine it's not here. Okay. So I have a state register. The state register content feeds back, as well as the inputs come. We feed it into this memory, the ROM, and the output of this memory is the state bits, the next state bits, as well as the output bits. The output bits go to the output, the state bits go to the state register. So this is our good old sequential circuit, and this memory is which is realizing that combinational logic we had. So I have I bits of input, S bits of state, O bits of output. So the memory will have S plus I bits of address, and it will have S plus O bits of output. Okay. And the size of this memory, well, it will have 2 to the power S plus I locations, and in each location I will have S plus O bits. So total number of bits in the memory is going to be 2 to the power S plus I times S plus O. Okay. So it's not very efficient. ROMs are never very efficient at implementing combinational logic, but they certainly kind of do the job. What about this guy? So this register that we see out here is basically, what it is saying is that you can think of the two registers together as being my state. And what is happening is, some of the bits of the state are basically feeding into the output. So this is this is to make sure that my output is very clean. This is often done, and in FISM they call that they have direct support for this kind of approach. So it's very commonly done that we make the outputs to be certain state bits, okay, and not come directly from the memory. Okay, so this way the output changes right at the clock tick. Whereas if output was coming out of the memory, or in our design, if output was coming like this, if you look at this design, the output will change whenever the clock tick comes. After that, I may have all this delay through the output block before the output changes. So there may be a significant delay from the clock tick to the point where the output changes. So by putting as in this design, putting this register out there, what we are doing is we are making sure that the output changes right at the clock tick. So just a very commonly used design practice, but this is nothing but a different way of looking at states. Okay. But main thing is I have this memory, and the advantage of memory is I want to change my state machine. I can just change the contents of the memory. If the memory is RAM, I can write new contents to it. If it is ROM, I'll need some special hardware, but I can still reprogram its content. So by reprogramming the memory, I can suddenly have an entirely different FSM. You don't have to go through this whole cycle of gates and wiring them up or stuff like that. You basically have a programmable finite state machine. And programmable finite state machine is what basically a computer is. Okay, so this is kind of the idea. So let's take an example. This is our, I think, slight adaptation perhaps of the traffic light controller, which was the very first FSM we had seen, which was controlling traffic light at the crossway. There was a sensor called car on east-west route, and then we were cycling through green north-south, yellow north-south, green east-west, yellow east-west, and these were the outputs. So like here, north-south is green and east-west is red. Here, north-south is yellow, east-west is still red, and then north-south becomes red out here, but east-west is green, and then finally east-west is yellow and north-south is red, and cycles back. So this was our very first state machine, and we had made, I think the TAs had shown in the discussion section that how we can implement it using gates and all. Let's see how you might do it using ROM. So this is a state transition diagram where I have 4 states. I have the states listed in symbolic form first. Then I put the state into a coded form. So I call the state to be 0, 0, 0, 1, 1, 1, and 1, 0. And then the next state depends upon the sensor output, car east-west, and then I have 6 bits of output. And until now, the approach we knew was we take this and essentially use Carnot maps or some other such tool to create the logic function corresponding to this. So I have 6 bits of output for the external world and 2 bits of next state. So I have total of 8 functions, 8 1-bit functions. Each one of them takes 2 bits of state and 1 bit of car east-west. So 3 bits coming in, 8 bits going out. That's what our system looks like. So what this microcode approach says is that let's think of the input to our combinational thing as an address. So address consists of 2 things now, 2 bits of state and 1 bit of car east-west. And output, that is a next state and the output to the external world, we are going to think of that as the data. So the data part of the memory has 2 elements to it, next state, which is 2 bits, and output, which is 6 bits. And now what we can do is we can map this thing into contents of the memory. So for example, at address 000, so firstly we know that address is 3 bits, so that means my memory has 8 locations. So I have a memory of 8 locations. At address 000, I have data 0010001. So the one which is, so if you, the color coding is the green 00 corresponds to state, the brown 0 corresponds to car east-west, and then on the data side, the first 2 bits correspond to next state, and the next 6 bits correspond to output. So it's saying if I'm at address address 0 in the memory, I have the content 001, 00000, whatever, 4 zeros and ones. Okay, that's what is sitting there. And what will happen is, this is the combinational part of the system. So when state is 0 and car east west is 0, then next state is 0 0, and north south is green and east west is red, which is what you see on this table on the left. So you have 0 0, and car east west is 0 is this guy. Next state is 0 0, and output is 1 0 0 1. And what do you think would be in the next address? Address number 1. Anyone wants to take a shot?
001.
Okay, so no, so that's the address. I meant what's the data? Okay, so state is so address is 0 0 1, right? So that means current state is 0 0, and car east west is 1. Okay, so now can anyone tell me what would be the content?
It would be 0 1 1 0 0 0 0.
Yeah, so 0 1 1 0 0 0 1. Okay, what about next one? So I'm now at address 2. So address 2 corresponds to what current state? 0 1, and car east west is 0. Okay, so looking out here, current state is 0 1, car east west is 0. That says next state is 1 1, and output is 0 1 0 0 0 1. Hopefully, if I didn't make any typo, that's what you should see out here. Okay, and so on and so forth. So this I can redraw or rewrite this table in terms of contents of the memory. Okay, it's just one-to-one mapping. It's just laid out in a different way. But the nice thing is that once I have this memory with these contents, then it acts like the combinational logic I wanted. I give it the input, state and car east west, and it gives me the output, next state, and the actual output to the system. So very cheap, quick, dirty way of making combinational logic, but we start thinking of it as address and data. Address is the value of the inputs to the combinational logic, and the data is the output values coming out of the combinational logic. So I guess at the end it kind of ends up looking something like this. So in Logisim, you can instantiate a ROM, and then you can edit its content, okay, and you can even read the content from a file and kind of do all of that magic out there. Okay, so now what our design does is it looks like this. Where I had the combinational logic before, now I have a memory, but the memory with this content. So it has memory with 3 bits of address, so it has 8 locations, and the contents of this memory are the ones which we just decided. Okay, you can sort of we literally take these contents and we put them out here. And then I have the 2 bits of state register, and I have 6 bits of output which is going to the light. This memory, if it is RAM, then I can rewrite it in software. If it is ROM, I have to make some extra effort, but I can still usually change the content. Okay, so because a lot of times these are reprogrammable using some special hardware. So now let's say I have the state machine and I decide that, hey, I want to change the logic for this. Then previously we would have to come up with a new gate implementation and all. Now all we do is we rewrite this content and I can change the behavior suddenly. Okay, so there are limitations for sure. I cannot change the number of states. Like I can have at most 4 states. I cannot have more than 4 states. And obviously I have 1 bit of input and 6 bit of output, but within the confines of that, maybe I can change some of the logic there. For example, maybe I might want to spin in some other state also based upon the sensor signal, things like that. So it gives us a programmability, and it gives us a general way of looking at things. Now, this thing begins to look like program. Okay, we'll see soon that we'll actually make it look very much like a program. How many of you have ever seen assembly language programming? So I see a fair number of hands going up, right? We'll see pretty rapidly. We'll see that it actually looks microcode. We can make it look very close to what programming in assembly kind of looks like. Okay, so any questions on this? So thus far, what we have done is we took combinational logic and we replaced it by ROM. and the contents of the ROM are basically copied from the truth table. Okay, so we are saving ourselves the headache of making the gate level netlist and all. Now let's see what advantage disadvantage it has. And again, as an aside, sometimes you will see this register being put out here, and this is again done so that the outputs going out are changing right at the clock tick. Now of course, relative to this, by putting this register, I have delayed my outputs by 1 clock tick. Okay, and that may or may not be fine, but usually it's a non-issue because clock cycles are so much more rapid than rest of the world. Okay, so let's say I want to uh, make changes to this thing. Okay, so for example, let's say I want to add some additional functions. I want thus far what was happening was when the car east-west sensor went high, we let the light be green for 1 clock tick. But let's say we want to modify so that we say the light should remain green as long as car east-west sensor is reporting there is a car. So if there is any car on east-west, we'll keep giving it, we will keep letting it go. Okay, so we get the priority. And then we can also say things like light can stay green in north-south direction for a minimum of 3 states. So if there is a lot of traffic on east-west, we still want to make sure that the north-south keeps getting some amount of time. And then maybe right now what was happening was when the light was turning yellow, in the next cycle the light would go red in this direction and turn green in the other direction. Maybe what we might want to do is, for safety reasons, we say that instead of going from yellow red to red green, maybe from yellow red we should go to red red and then to red green. Okay, so we want to add some safety in each direction. So these are all reasonable things to one might expect changes to be made to the specification. So let's create a state machine which has all these changes. Okay, so now what we have is we start out with green north south 1. We stay in this state for at least 3 clock cycles. Okay, so that is our new requirement number 2. So I stay in GNS1, GNS2, GNS3. Once we are in GNS3, then we check car east-west. If car east-west is high, I go to yellow north-south. Then I go to red north-south. Then I go to green east-west. And then I keep spinning here as long as there are cars on the east-west direction, and only when I come out I go to yellow east-west and red east-west and go back. So one thing you notice out here, I have this state called RNS and this state called REW, where both the lights are red. This corresponds to, in the previous cycle, previous slide, bullet number 3. And this one out here where I'm looping corresponds to bullet number 1. So this is a state diagram which incorporates these 3 changes. Any questions? Yeah.
Is there a way to add like having a state in multiple clock cycles without adding multiple states?
No. Okay, so my quick answer was no, but anyone wants to suggest some? We saw one way of doing it last time. Counter. So remember we had a counter with a done signal, and that would let us spin. So the idea is when you enter the state, you initialize the counter, and then you spin on its done signal. Okay, but in a way, all we are doing is we are cheating. We are basically, instead of having states here, we have the states in the counter. Okay, but you can. Okay, did everyone get that question? So his question was, look here, how to spend time in the same state. I actually have 3 states listed. Okay, what if I had 100 states to be done? What would I have done? Would I have 100 states out here? Well, at some stage it becomes better to farm it out to a counter. Okay, but for something like this, it's better to do it here. Just small number. I think when we were doing back there, we had I forget, but this was a lock example, and we were locking out the user after he had entered the incorrect password for a long period of time. Okay, so there it made sense to have a separate counter timer, whatever you want to call it. Yeah. Any other question on this? So all we have done here is just modified the spec, and I want to walk you through how we might do a microcode for something like this. So go ahead.
Like, would it be possible to instead of like a counter, individually change like the clock frequencies for one or these?
No.
Okay.
I mean, okay, possible in theory, yes, bad practice.
Okay.
Okay, actually, that reminds me of something which I also intended to say, which is do not make use of asynchronous set reset of flip-flops and counters and stuff like that as you are doing the current design assignment. You are going to be you're going to regret it. Okay, in terms of you'll probably drown in the complexity of your own design. Okay, so that apart, it's bad design practice. So, okay, so keep things. Essentially, your master clock is the one which should feed to all the clocks in any flip-flop and any counter, and do not mess with it, and do not make use of synchronous set resets, other than to initialize the circuit, bring it to a null state. Okay, so do not use it, do these things to generate freaky looking pulses and stuff like that to do some logic. Okay, that's just going to cause problems. Okay, back to this questions again. Okay, so let's see how it works out. And kind of the intent is you will see that this will again look like a program. And so now suddenly we'll switch from the mindset of that, I have memory and I go from state transition diagram to this to one where we'll say I have memory and I'm going to translate this thing into code. Okay, so this is what it's going to do. Now I have a bigger memory, obviously, because I have a lot more states. I have 8 states at least in terms of the way I'll code it, and I may actually will see that we may end up having more. So certainly my S goes to 3. So let's see what might happen. So I now have 3 bits of state and I have 1 bit of input. So I have 4 bits of input to my combinational logic. So my memory, the ROM is going to have 4 bits of address. So there are 16 slots in the memory. And each address could be interpreted as a value of the current state and a value for car east west. So for example, address 0010 is 001. The first 3 bits are the state and the final bit is the value for car east west. And we are going to label these things with now if you look at the first 2 addresses 000 and 0000 and 0001, the current state bit is the same. So that's why you see the current state is the same, but they differ in the value for the input. And then on each location I'm going to have the value for the lights control, so 6 bits there, and I also need values for the next state, which is 3 bits. So you see next state, which is 3 bits, and you have output, which is 6 bits. These together will form data, which is going to be 9 bits. So previously we had 8 memory locations, each one of them with 8 bits of data. Now for this new state machine, I have 16 memory locations and each one of them with 9 bits of data. So I have 144 bits now, whereas previously I had 64 bits. Okay, so a much bigger memory, almost more than two times as big, but then of course it has increased functionality. And you'll have to trust me on this, that this essentially codes this previous state machine, but let's verify one of them. Let's say we look at GNS3. So GNS3 we decided to code as 010. So in address 0100, I will have what is happening when I'm in GNS3 and car east west is 0. And in address 0101, I will see what if I'm in state GNS3 and car east west is 1. So if we go back out here, I'm in GNS3. If car east west is 0, I stay there. And if car east west is high, I go to YNS. You will see the same thing out here. If I'm in GNS3 and car east west is 0, next state is GNS3. If car east west is high, next state is YNS, and YNS is coded as 011. And then the outputs in both cases, since it is GNS, it's 100001. So these two together give me the data part out here. So I can essentially, by looking at this, I can kind of write down the contents of this memory by essentially systematically translating every transition and every possible output into the contents out here. And I can rewrite a new state machine by just changing these contents. Any question, doubts on this far, thus far what we have done? Do you see any problems with this approach of ROM? What kind of issues do you think this design approach, what were our disadvantages? Yeah. If you don't have, yeah, so if you have don't care, I cannot reduce my logic. Great. Absolutely. So the point is, I have to put that amount of memory, right? Okay, so don't care translates into the content being don't care as opposed to gates not being there. Okay. What else? Anyone else can think of other issues?
You could potentially have a really, really large address space if you have a bunch of, or actually just more states.
Yeah, so you're touching up. So let's say, so in this case, uh, I have 4 bits of addresses, and I had 8 states, and that fitted perfectly well. What if I had a state machine with only 7 states? Right, so it kind of goes back to the don't care point that was being made, that some of these rows are going to be unnecessary. Now, unfortunately, memories always come in sizes which are power of 2, because they take s bits of addresses and they will have 2 to the power s slots. So even if I'm not fully utilizing it, so let's say I had only 7 states, 2 of these rows will be underutilized. I'll have to put some junk content there, but I cannot reduce the size of the memory. So memory can be rather inefficient to use because of this reason. Okay. So the issue that begins to happen is, if you see the size of the memory, going back a few slides, it had said number of bits in the memory is 2 to the power s plus I times s plus O. S was number of state bits, I was number of input bits, O was number of output bits. So this is what it had looked like: 2 to the power s plus I times s plus O. So what you see out here is, if I have lots of inputs, size of memory increases exponentially. Okay, so if, let's say, I added a second sensor to that example for north-south, then suddenly, instead of 16 memory with 16 slots, I will need memory with 32 slots, twice the size. The other thing you would notice is, the input matters only in very few states. It's not as if I'm using the input in all the states. In fact, if you look at my table out here, in most states, it does not matter whether car east west does not matter, whether it's 0 or 1. So like if you look at the first 2 rows, they are actually identical, other than the fact that car east west is 0 in one and 1 in another. So there are only 2 states in our example where car east west actually had a role to play. Everywhere else, I had 2 identical rows, 2 identical pieces of data, which again seems very, very wasteful. So the memory approach, while very flexible, is, if implemented this particular way, leads to lots of problems. That essentially every time I add one more bit of input, immediately means twice the memory size. So the trick then became, can I reduce this memory size? Can I play games with the way we organize the data, perhaps with some other cost? Maybe now I'll have a slower design or something like that, but could I reduce the memory size? Because right now we are wasting so many bits. So there are few observations which are made out here. One is, most of the time we move from one state to the next one, numerically the next one. Okay. In fact, if you see out here, the way we had coded, these states were all in sequence. So most of the time I'm just moving from state 0 to 1, 1 to 2, 2 to 3, 3 to 4. We're kind of just moving in sequence. What does that remind you? Yeah, and so, like, do you see software, program counter, instruction pointer? It just moves, unless you do jump or while, it just moves from one to another, right? So So you're right, it's a counter, specialized counter, but whose role is saying, where am I? Okay. So it kind of suggests that, if most of the time I'm going to be moving from from current state to that is next state is state plus one, then why do I need to store all the bits in the memory? Why not simply put an adder out there? Okay, that way I don't have to store these things in the memory, because most of the time I'm just saying the bits corresponding to next state are basically one more than the bits corresponding to the current state, so which is kind of wasteful. And the other observation is we usually need to branch from one state to another one only with making use of very few inputs. So what is meant by this is that if you look at, like when you write the program, you will probably have a bunch of if statements at various places in the program, and they will make use of some variables. But not all variables are used in every if statement. So it's not like, so firstly, we are not branching most of the time. Most of the time, we are just moving from one statement to next statement. And the next observation is, even when we do branch, we make that decision based upon a small number of inputs, not all the inputs. In the example thus far, I had only one input, so it didn't really matter. But so you can see that most of the time I'm moving one state to next. Only in two of the states I'm branching. I have some sort of a conditional, and that conditional just depends upon one input. So we'll see how to make use of that. So the key idea is, why have an explicit next state field? Why not eliminate that, save some bits, and save memory, incredible amount of memory, because if I save one bit of state, storing one bit of state in the memory, how much memory bits will I save? Anyone? Nothing deep out here. I'm just seeing whether you're up. Huh?
Do you have it?
You won't have it. So, okay. So if one bit of next state I'm saving, not right. So I'm saving my data size is going down by one bit. Okay. My number of state bits is still the same. It's just that I'm not storing all of them in the next state field. Okay. So if I save one bit there, then in each location I'm saving, so I'll save 2 to the power s plus I bits. Okay. So idea is that instead of, see how here my next state was 3 bits throughout, maybe I can get away with fewer bits. Okay. Even though my state, I still need 8 states, but I don't need to store the entire next state address out here. Maybe I can store fewer bits. We'll see how it can be done shortly. So the trick out here is, and this is much like what happens in software, we are going to introduce a counter called microprogram counter, micro PC. It's a special register, and all this register does is that it basically it holds the value for the next state. So now instead of listing the next state in my table, all I will do is I'll tell the counter increment or do not increment. Okay, so if you look out here in this design, when I reach DNS3, in software, how would you write this thing? You will say, if car east-west is 0, stay put, otherwise move to the next state, right? So this thing essentially is saying, if car east-west equal to 0, stay put, that is next state is current state, else next state is equal to state plus 1, because the way we have coded this guy is numerically 1 higher. So imagine if we had a counter available like this, to which I can tell on every clock tick, increment or do not increment. Then I can easily handle things like move to the next state. Move to the next state means increment, and stay put means do not increment. Okay, and microprogram counter holds the value of the state. Okay, so this is a special state register which has an incrementer built in. So most of the times we'll be incrementing, but occasionally we will not increment or perhaps load it with a new value. I want to jump to totally different next state. Okay, so that's kind of the concept. We can realize it in this particular way. So what we have out here is again our good old design where I have memory. This is my state register. So so what we are doing out here, so the state register um, is telling me where to get the next, uh, what is the next memory address to work from. Okay, so this will have some content, and we're going to call it micro PC. And we have three possibilities for controlling it. So there is a multiplexer out here. This guy says that the value of the new value of micro PC, so which we have called it as NUPC, new micro PC, it can have one of three values. It can either be current value of micro PC plus 1, or it could be 0, which basically means go to address 0, or it could get its value from a target out here. Okay, that is in the memory I have S bits of state. So we're going to work through this thing. So right now imagine that I still have the next state field. So I get this branch target and I feed it back out here. So micro PC can take three values. Micro PC can either take the next state field from the memory, or it can be one more than the current micro PC, or it could be 0. And then I have this combinational logic which takes my inputs and which also takes some additional input from the memory and then controls this multiplexer. So the idea is that my instruction in the memory, if I look at the memory instruction, it will have next state, that would be S bits. It would have B bits of branch, and it will have O bits of output. So each memory location has three fields in it. It has S bits of next state. Think of it as the next address. Okay. B bits of some special bits which we call as branch instructions, which is what we have out here. And I have O bits of output. So I've introduced two new concepts in this diagram. One is I have this whole micro PC stuff. The other is I have added these additional bits, the B bits, which I'm calling as the branch bits. And output is what controls which goes out, which we already had. And these S bits are like what we used to have before. Okay, so now what we can do with this thing is by appropriately controlling what is in those B bits, what we put out here, and what the inputs are. Using that, I can control this multiplexer. So let's say, for example, I could say micro PC should increment by 1. Then perhaps some special combination of branch instruction will do that. Or I could say micro PC should get the value 0. Then again, some special combination of branch instruction can do that. Or I can say micro PC should get the value which was the content of the memory in this field, the NS field. Then again, some appropriate value of branch instruction could arrange to do that. We'll see how to make that happen very shortly. But conceptually, what we are trying to arrive at is a little bit like the way we do it in programming things, where we are saying if the BR bits, if this field and input meet some condition, that is, if some function f of BR, by BR I mean these branch instructions, so this is the same thing. If some function of BR and inputs equal to true, then micro PC is equal to one of these three options. It can either take the value plus 1, so it could be either plus 1, or it could get the value 0, or it could get the value next state, one of these possibilities. So so I can define some sort of a logic like that through branch logic. Let me try to do it through an example. So again, going to the memory. In the memory, I have three fields sitting now. I have at each address of the memory, I have B bits of what I'm calling as the branch instruction. I have S bits of what I'm calling as a branch target, and I have O bits of the output. This is what we used to call as next state. And this is something new. Okay, this we didn't have before. So we have just redefined the contents of the memory. And at every clock tick, I go to that location of the memory which corresponds to micro PC. And at every clock tick, I have three options. I can increment micro PC by 1. I can load 0 into micro PC, or I can load into micro PC the contents of this branch target or the next state field. So now the magic happens in the branch logic. So let's imagine my branch logic, the combinational logic which I have out here, looks like the following. What I let's try with something simple. Let's say I didn't ignore the input. Let's say my branch input said the following. My branch instruction had 2 bits. Let's say b equal to 2. And let's say these were the possible values: 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1 there. You can take 4 values. Let's say this never occurs, so I never use this. So let's say these are 3 values. So when BR is equal to 0, 0, I basically say select this input, 0. When BR is 0, 1, I say select 1. And when BR is 1, 0, let's say I select 2. So how would I express a next state be such that microprogram counter goes to the first address of the memory, the address 0? I would basically make sure that in the current instruction, the bits for BR are 0, 0. Okay, so this corresponds to 0, this corresponds to 1, and this corresponds to 2. So if I want to, so it would be 1, 0. So if I want to stay put, if I want to go microprogram counter to become 0, then I'm going to ensure that the branch field says 1, 0. If I want to go to the next numerically next state, what would I do? What would the branch field be? It would be 0, 0. And then finally, if I want to jump to a random location, let's say I want to jump to address 10. So next state is 10. Okay, what would I do? So BR is going to be 0, 1 because I want to select the middle one, and I'll have to put 10 in the branch target. Okay, so essentially it's saying, so we take this branch instruction, we combine it with the input. Right now in my example, input didn't matter. Whatever this logic is going to select one of these 3 inputs, and then the microprogram counter will reflect that. So if I want to go to address 0, I arrange this output to be such that 2 is selected. If I want to go to a random state, I make this thing so that the middle one is selected. And if I want to go to the next state, I select this one. What if I want to stay in the same state? What would you do? So remember, in the example we had, if car east west was 0, I want it to stay put. Okay, so my question is, what would you do in this example so that microprogram counter does not change its value? I want to say, anyone from this side? How would you approach this? So given this functionality where microprogram counter can do one of 3 things. It can increment by 1, it can jump to the contents of what the next state said, that is this field, the branch target, or it could be made 0. My question is, I want microprogram counter to remain unchanged. Huh? Branch target will be the current address. Okay, is that clear to everyone? So imagine here, if branch target was the current state, then and I arranged the branch instruction so that it selected the middle one, then I'm going to stay put. What if I want to jump to not the next state, but the state after that? Same approach. I will arrange for branch target to select the middle one, but set branch target to be a state which is numerically 2 higher. Okay, so it's kind of like in many programming languages you have an instruction called go to. So I'm basically saying go to certain place in the program. So I can do that I can certainly increment by 1, so I could do that, and I can do 0. Now this example is contrived and stupid. Do anyone see the stupidity in this thing? Don't be ashamed. Go ahead.
Because you don't really need the multiplexer before the branch instruction bits if you just make the branch target.
Right. I mean, if I'm putting all these S bits out here, and then why not just always encode it, right? So thus far, I have not gained anything in this exercise, right? I'm still carrying the entire S bits. Okay, I started out with the story that I want to save on those S bits, but I'm still having those S bits. Okay, so it's not really buying us anything, but we'll see shortly why it does buy us something. Okay, but thus far, this is not bringing us any closer. But nevertheless, one thing you would notice out here is that the number of bits in the memory out here are going to be 2 to the power s, where s is the number of address bits. And then in each location, I have s bits of branch target, o bits of output, and b bit of branch instruction. So this is the number of bits I have. The inputs are sitting out here. Okay, so one nice thing out here is that my memory size no longer depends upon the number of inputs. See, previously, how many words did I have in the memory? How many slots? What was the number of bits of addresses we had? S plus I. Recall that? 2, that's why we had 2 to the power S plus I. But now the inputs are being handled out here. Okay, so I have the supporting logic where all these things, branch instruction together with the input is doing that. So like for example, I could do something like the following. Let's say I wanted to say within this framework, I want to say if so let's say I had only one input, car east west. I want to say if car east west is high, go to the next state. Otherwise, stay put. Okay, did you get it? So car east west is high. I want to go to the state plus 1. Otherwise, I want to stay where I am. Using this machinery, do you think you can make that happen? Anyone wants to give a shot? I want to, depending upon car east west, if car east west is high, I want microprogram counter to increment by 1. If car east west is low, I want microprogram counter to remain unchanged. Yeah, you guys answer too much. So I'm really hoping someone from this side. Let's simplify it further. Okay, so let's say I want to achieve the goal that if car east west is 0, I want to stay put.
There's another path
Hmm?
in your box.
No, you don't need another path. All you have is this. But remember, you have this branch logic. You can put any logic out here. Yeah, you might be done.
Okay, so because you just want the input low to select 0, right?
Yeah, so if car east west is 0,
You want to select 0. So
I want to select, if car east west is 0, I want to stay put. So I want microprogram counter to retain its current value.
Okay, so that means we use a NOT gate to the input to connect to the. Yeah, so the branch target is supposed to be your current state.
So branch target would be current state.
And then because you want the input to be low to stay in your current state, so
I want to select the middle input.
So I want to select the middle input.
Okay, so I need to make this logic so that if car east west is high, sorry, if car east west is low, and branch instruction has the right value, then the middle input is selected.
So it's like an AND.
Well, there will be some logic out here, okay? And if car east west is high, then I want branch logic to select the first input because I want to move to the next guy. So what I've done is I put part of the burden on the branch logic now. The branch logic has to be intelligent to kind of take into account this, what the inputs are doing together with these branch instructions. Let's see if I have some. Okay, let's imagine the following. Let's say my branch logic implemented the following. So for a moment, imagine that I have a modified version of this design where I do not have this third choice. So I don't have the choice for 0. I only have 2 choices. I can move to the next state or I can jump to a random state. Now imagine my branch logic selects between these 2 possibilities, this and the branch target, depending upon input and branch instruction. So I have branch instruction B bits and I have I bits of input. And what my branch logic does is, depending upon the value of these 2 bits, it makes the microprogram counter either to be equal to branch target or to be equal to my current value plus 1. So what I can do with this thing is the following. I could make many different kind of instructions by having appropriate coding of these bits out here. So let's see how it might work out. So let's imagine I want instructions of the following form. I say branch if input satisfies some condition. So like for example, I want to say branch if car east west is high. Otherwise, stay put or move to the next instruction. Branch if car east west is 0. Otherwise, go to the next instruction. So these are basically saying if some condition is met, jumped to a new state. Otherwise, move to the next state. So implied out here is otherwise go to next state. So what this instruction is doing is branch if f of input, some function of input is true, is it's basically saying if f inputs is true, then micro PC gets the value branch target. Otherwise, it gets the value micro PC plus 1. Let's say this is what I seek to implement. Okay, this would be a very useful functionality to have because in a program, at any place I can say if condition is true, go to somewhere else. If condition is false, I move to the next instruction. How would you implement something like this? So let's back up. Using this, let's say I want to implement this kind of a logic. I'm in a state. If car east west is false, I stay put. If car east west is true, I move to the next state. So I'm in a current state. Next state would be the current state plus car east west. Why do you say that? Okay, fair enough. Next state is car east west plus 1. Okay, but I cannot implement it that way, right? Because I only have control over the multiplexer. So let's I have a mux, I have micro PC. This is one possibility. The other possibility is branch target. I'm seeking to control this guy. So this is what it looks like. I have a micro PC. Micro PC plus 1 would be here. Micro PC gets the value, branch target would be here. We are trying to design this control circuit. It is getting one input called car east west. It is also getting an additional input, which is some sort of a branch instruction. So let's call it BR, a single bit. So what we want to do is we are basically trying to say that if BR is high and car east west, so it's a branch instruction, so BR is high and car east west is high, then we want to jump to the next instruction. Otherwise, I want to jump. Otherwise, I want to jump to the branch target. So what I want to do is, if branch and car east west equal to high, then micro PC equal to micro PC plus 1, else branch target. So what I want to do is, if it's a branch instruction, if car east west is high, then increment, otherwise stay put. What would happen in this logic? And I have a single bit out here. I want someone on from that side. This is our first half of the course. Okay, so I want this bit to select something from this multiplexer based upon these two inputs. What would this logic look like? NAND. Okay, so if I do a NAND, then firstly I want it to be enabled if it is branch, so that is true. And then if car east west is also high, then it is going to select 0, and that will take us plus 1. So NAND would work. Let's try something different. If I want to switch it, if I were to say, if car east west is 0, someone from that side of the room, I am just changing that. Car east west is 0. I want program counter to be incremented. Come on, guys. Someone from that end. Again, this is lecture 3 material, so please. What logic would I put out here to implement what is sitting on the right hand side? No, but I can take her NAND gate and put an inverter on one of the inputs. Right? I could do that. Okay, so I guess the point I'm trying to make out here is that by putting logic out here, I can affect the behavior of how microprogram counter is going to be updated. So when I'm designing now, I have not only control over the memory content, but I also have control over what is happening out here. And by the way, I get to define what those branch instructions are, because everything is under my control. Those are just magical fields. I just declared that some bits out here, I'm going to call them as branch instruction. And the role they are playing is they're feeding into this logic out here. You are in overall control of the as a designer. So let's see how one might do in a design. So let's imagine I have 2 bits of input, in1 and in0, And let's say I decided I'm going to have 3 bits of branch instruction, and I'm branch instruction 0 through 2. And let's imagine that that logic that I have, that I was just talking about, this 1 bit that we are providing, let's imagine that logic implemented this function. It implemented that output of my logic is branch instruction 0 and in 0, or branch instruction 1 and in 1, the whole thing XORed with branch instruction 2. Okay, and let's say, just humor me, and let's imagine this is the logic. And let's see now what will happen. So let's imagine that branch instruction was all 0. So somewhere in the memory, in the current state, branch instruction was 0, 0, 0. Now if you look at it, what will happen in this logic? Branch instruction is 0, so this is 0, so this AND disappears. Branch instruction 1 is 0, so this disappears. So I have 0 or 0. So this whole thing would be 0. 0 XOR branch instruction 2. Well, branch instruction 2 is also 0, so I have 0 XOR 0, which is 0. So it will select value 0 out here, which would be the incrementer. So it basically says, don't branch, proceed to the next state. Let's imagine branch instruction is 0, 0, 1. So in that case, branch instruction 0 is 0, branch instruction 1 is 0, so this initial part is all 0, but this guy is 1. Sorry, did I misplace something? It's 0. Oh, so am I? Yeah, this guy is 1. I'm sorry. This one is 1 and this guy is 0. Okay, so what I have is this term is 0, so that OR 0 disappears. This guy is 1, so this is in 0. So it's 0 in 0 XOR 0. In 0 XOR 0 is in 0. So it's basically saying branch if in 0 is 1. Okay, because if in 0 is 1, then in the multiplexer, the lower value would be selected. If in 0 is 0, it would be the upper value. Let's take another one. 1, 0, 0. 1, 0, 0 means branch instruction is 0. So this guy is 0. Branch instruction 1 is also 0, and this guy is 1. So this whole thing is 0. 0 XOR 1 is 1. So the output would be 1, and which would mean always select the lower part, so it will always branch. Or take another example. Let's say 1, 1, 1. So if it is 1, 1, 1, I would have in 0, because this is 1, or in 1, the whole thing XORed with 1. So that means in 0 and in 0 or in 1 complemented, which basically translates into branch if neither in 0 or in 1 is 1. And each one of these cases are covering different useful situations. So let's say I wanted to do so firstly, which one of these encodings you are going to use if you just want to proceed in a normal state? I just want to move from one state to another state. The very first one, no, so no branching taking place. If I want to encode an instruction in the form, go to state 10, what would I put into my micro instruction? I see your hand raised. I'm not going to call on you. I know you know. Okay, anyone? Back of the room, guys, there. So looking at this table, let's say I want to jump to state 10. My question is, what would my micro instruction look like? What would I put in branch instruction? What would I put in branch target? If this is what I have. So again, I want to just unconditionally move to state 10. So branch instruction would be 0, 1, 1, and branch target would be that numeric value for 10. Okay. Let's say let's imagine that I want to say if input 0 is 0, stay put. If input 0 is 1, move to the next state.
I think you move to the next slide.
Oops, sorry. Okay, so if input 0 is 0, I want to stay put. If input 0 is 1, I move to the next state. Carrie, how about you? So again, input 0 is 0, I want to stay put. Input 0 is 1, I want to move to the next state. So actually this one is trickier, so maybe wrong person. Okay, let's try some of this. You want to do it?
You would use 101.
Okay, so we are going to use 101. So 101 says that if input 0 is 0, we branch.
You would branch to the current state.
Branch to self. Okay, so the suggestion out here is I'm going to use this guy. So remember, my logic was if input 0 was 0, I want to stay put. Otherwise, I move to the next state. This guy achieves it because I can say if input 0 is 0, branch to self, our own address. And if input 0 is high, it will move to the next address. So it's kind of like saying some label, go to whatever, some address, go to my own address. Okay, with that. Let's try something else. Let's try the other way around. So now again, I'll come back to you. If input 0 is high, I want to stay put. Otherwise, I want to jump to the next state. Paulina, you want to try? So again, if input 0 is high, I want to stay put. Input 0 is low, I want to move to the next state.
0, 0, 1.
Yeah, 0, 0, 1. Okay. Actually, if you look through these things, you can see that most common patterns I can do. Okay, let's try another one. If input 0 is 1 and input 1 is 1, I want to stay put. Let's see, can I do that? Okay, let's try a simpler one first. So let's imagine input 0 and input 1 were connected to two sensors. And what I want to do is I want to say if either one of the sensors are reporting an event, that is, they are high, then I want to move to the next state. Otherwise, I want to stay put. So I want to wait in my current state if neither one of the sensor is reporting any event. But if any one of them is reporting an event, I want to move to the next state. Which branch instruction will you use? 1, 1, 1. Branch if neither input 0 or 1 is 1, right? I mean, if any one of them is 1, I move to the next state, otherwise stay put. Almost any useful thing you can think of involving in 0, in 1 and all can probably be mapped out here. Message I want to give is that a carefully designed branch logic can implement many different possibilities for staying put, moving to the next state, or jumping to a random state. These are the three possible patterns that you would see and which are sufficient. So jump to the next state, jump to a random state, and jump to or stay put. So jump to self. Now, have I still addressed my problem of still needing S bits? I still haven't gotten rid of that possibility. I still need S bits of going back out here. I still need S bits of branch target, so which is still painful. But nevertheless I gained. Going back out here, my memory size is 2 to the power S plus O plus B, whereas originally my memory size was 2 to the power S plus I times S plus O. Under what condition do you think I am better off? Well, if you think about it, I have increased the number of bits in every word, but I have reduced the number of memory words by 2 to the power I. So I have an exponential reduction in number of memory words, but I have an increase in the number of bits in every word. So I'll likely be better off with this approach already, but it would be nice still if we can reduce, if we didn't have to carry this entire S most of the time, because most of the time it is actually superfluous. Let's try another example. Let's say my same setting, I had two inputs. I had 2 bits of input, so I'm messing it up obviously out here. 2 bits of input and 3 bits of branch instruction. And my encoding was that branch, if branch is true, that is branch is 1, if branch instruction 3 and can anyone tell me what this guy means? How would you faced in a if I were to just give you that, what how would you interpret that?
You're selecting the input based on the branch instruction, the one you're concerned about.
Correct. I'm selecting the input based upon the branch instruction. So I'm looking at the lower 3 bits of, I'm looking at the 3 bit of branch instruction. That can take, I'm messing things up out here obviously. Let's see.
8 inputs then?
Yeah, I have branch instruction 3. Yeah, it's branch instruction 1:0, and this should be 2. Okay, a lot of errors out here on this slide. Sorry. So this should be 2, and this should be 1:0. Okay, so what's going on out here is we are looking at the lower 2 bits of branch instruction. They will correspond to the value 0 or 1 or 2 or 3. And we are selecting that input because there are and this is 3. This was correct. So I have 4 inputs. Uh, 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 I have let's see.
You're only using 3 though.
Input 0, input 1, input 2, input 3. So I have 4 input values. So, and I'm using all 4 of them. Yeah, this is correct, right? I mean, so branch instruction 1:0 is going to take values from 0 through 3. And I'm selecting that input number. Okay, there are 4 possible inputs. Input 0, there is a wire call input 0, there's a wire call input 1, there's a wire call input 2, and wire call input 3. And I'm selecting that one. So it's basically saying branch if the input is selected by the lower 2 bits of branch instruction, and then I'm taking that input and I'm going to AND it with branch instruction 2. So let's look at this guy, 0, 0, 0. If branch instruction is 0, 0, 0, then branch instruction 2 is 0. So 0 and nothing matters. So okay, obviously I have totally messed up this example. Encoding 0, 0, 0. Okay, let's ignore this one. Obviously, I messed things up quite a bit. Okay, let's try something else. Yeah.
I think if you change that the AND to a 4.
Yeah, it's just that I'm changing everything, so I'm not sure whether. Okay, let's see. Let's try a suggestion. Let's try this guy. try this guy to OR. Okay, let's work it out. Okay, so let's say again encoding 000. So branch instruction 2 is 0. So this 0 disappears. I'm left with input selected by branch instruction 1 colon 0, which is also 00. So that says branch on input 0. Okay. 001, branch instruction 2 is 0. So that disappears. Input selected by 01. So branch on input 1, that works. Branch on input 2 also works. 011, that branch always, if input 3 is tied to constant 1, so we have input 3. Yeah, go ahead.
But that's going to break for the rest of them. It needs to be stored.
XOR. You know, I'll send out a revised version of this slide, but let's move on. Okay, so let's now go back to our revised state machine that we previously had. We have, so again, recall in this case, we had made 3 changes. One was we wanted to spend 3 cycles on north-south. We also had states where both lights were red, and we were staying put on east-west green as long as there were cars. So those were the 3 cases which are going on. And now let's imagine we want to make some further changes in this thing. Okay, so let's imagine I have created a micro-coded FSM. I've set up the branch instructions so that I have these instructions available to me. So I have an instruction called NOP. I have an instruction called branch. I have an instruction called branch left turn, branch not left turn, branch east-west, and branch not east-west. So the idea is now I have 2 additional, I have 2 sensors. There is an east-west sensor, and there is also a left turn sensor, so which is basically a car trying to make a left turn. And then I have arranged my branch logic such that I have these instructions available to me, and they have these encoding. So if the encoding is 000, it always goes to the next instruction. If the encoding is 100, it always branches. If the encoding is 001, then it branches if left turn sensor detects a car. If 101, then if no left turn, and so on and so forth. So let's say these were given to us. So the strategy is, faced with a problem, first thing you will decide is, what kind of branch logic do I need? Okay, I can get away with some simple branch logic or something very specific to our problem, something which is general purpose, or maybe no branch logic at all. Maybe all I have is jump to a state that I specify. So let's say I had this. So how could I encode a state machine with a traffic light controller with a left turn? So I can kind of write a program now. So let's try to interpret it again. So what I have out here is state machine, the contents of the memory, and I'm giving these things names. So address 00, I call it as NS1. Address 1, I call it NS2. Address 10, I call it east-west 1, east-west 2, east-west 3, LT1, LT2, and LT3. And then what I do out here is I put the instructions. So this is the B branch instruction field, this is a target, and this is the output. So this is B bits, this is S bits, and this is the O bits. So what I'm saying out here is, the first state I'm saying is branch if left turn. So if left turn is true, go to LT1, and in the current state, this is the light. So I have so branch if less than, go to LT1. So if you see out here, this is Okay, so in the very first state, I'm saying branch if left turn signal is there, so that's the branch instruction 001, and what you see out here is 001. The target of my branch is LT1, which is this state, whose address is 0101. So you see out here 0101 being listed out here, and then finally I'm going to have the rest of the data bits, which are basically going to be my output bits, but let's focus on these two for now. Then on LT1, I have this saying no op. So no op means that I'm always going to move to the next state. So in that case, target doesn't matter. It's no op. So what you see out here is that the first 3 bits are 0, 0, 0, and then I have a bunch of zeros. State 2 says, so if I'm in state 1, if branch less than branch left turn, branch if left turn, I move there. Otherwise, I move to the next state. Next state is NS2, and so on and so forth. Let's try to draw its diagram. So let's say I'm in state NS1. Another state is NS2. Third state is EW1. Fourth this state is EW2, EW3. Let me use a new slide just to be easier. Okay, so what I want is your help in filling out the transitions. So we start with NS1. What are the transitions out of NS1? So one transition says that branch if left turned go to LT1. The other transition says move to the next state. So from NS1, I will move to LT1 if LT is true. Otherwise, I'll move to next state. So LT is not true. That is what this thing is coding. Okay, so it's basically saying branch if left turn, go to LT1, otherwise move to the next state. Next state is NS2. Here we are saying branch if not east-west to NS1. So east-west, we have two sensors, LT and EW. So it's saying branch if not east-west to NS1. So out here we have if not east-west, we go back. What happens otherwise? So I'm NS2 branch if not east-west to go to NS1. What would be the other transition? What if east-west is true? Next state, so it will go to east-west 1. So what happens in east-west 1? It's no op, so it always goes to east-west 2. From east-west 2, what's the transition? Anyone from that side of the room wants to help me out? So I am in state east-west 2. What would be the transitions out of it? So what is this instruction saying? BEW, let's go back out here. BEW, branch when east-west car is detected. So branch if east-west car is detected, and where are we branching to? East-west 2. So we are looping back, we are staying put. So what would the transition here look like? Self loop, what would I put here? EW. And if east-west is false, next state. Let's try EW3. So if I'm in east-west 3, what is happening? Always branch to NS1. So from east-west 3, we are always branching to NS1. Let's go to LT1. LT1, what is happening? We have a no-op. So what will happen here? We just go to LT2. Always. What happens in LT2? LT2 says BLT LT2. Loop back under what conditions? LT. Then LT, otherwise we move to LT3. And what is happening in LT3? Branch to NS1. So we go to NS1. Okay, now looking at the state machine, can you tell me what's going on at a very high level? So we start out here.
If you're at north-south and there's a car that wants to turn left, then you go to left turn.
I go through a left turn sequence.
And if there's still cars that want to turn left, you stay there. Once
Good.
there's not anymore, you go back to north-south.
Okay.
And if while you're in north-south, if it becomes there's somebody waiting east-west, then you go to east-west, and it doesn't matter if there's somebody who wants to turn left. You stay in east-west as long as there's a car in east-west. And if there's not, then you go back.
Okay, good. Did everyone so what's going on out here is we're starting on north-south thing. So we are basically giving our default is we are letting traffic go in the north-south direction. If the left turn light was high, I move to left turn, presumably turn on a left turn signal, and I stay put there as long as the left turn sensor keeps saying there's a car. And we keep doing it. When the sensor reports no car, I go back to NS1. So this is kind of my default state. If, on the other hand, there was no left turn car and there was a east-west car, I do the same thing with the east-west light. So idea is I have 3 sets of light out here. There is an east-west light, there is a north-south set of light, and there's a left turn light, kind of a red-green arrow, and I'm dealing with those. A question back there.
What is the purpose of the east-west 3 and left turn 3 states?
Okay, so what's the purpose of the left turn 3 state? Can anyone tell me? So presumably, I mean, I guess the problem here was if you look at the output, it will actually go through the yellow or the red state out there. So it's just giving you time for that.
Then,
So we are green here, but we are going to go through a transition out here.
okay, so then what about the north-south? Would the yellow transition be when you move from north-south to east-west 1?
The yellow transition would be when you move from north. So north-south is green. I guess we would have a yellow transition going on out here on the input state. Yeah, we can check out here what is happening. So we have east-west. So these. So let's see what's happening. So in north-south state, north-south is green, left turn is red, east-west is red. If I go to LT1, north-south is yellow, but east-west and left turn are both red. Okay, so that's what's happening out here. So this column is giving me the outputs. So essentially in this state, I'm turning yellow and I'm coming out of it. Let's look at out here one thing. See the structure NS1 and NS2 and how I'm first checking LT bar and then check LT and then checking east-west. In a normal state machine, I could have been sitting out here and just have an arrow saying if LT go here, if east-west go in a different direction. But with the branch instruction, the problem we have is I cannot simultaneously check both east-west and left turn. I cannot say, at least with this set of branch instruction, I cannot say if east-west is true and left turn is not true, then go east-west. If left turn is true and east-west is not true, go in another direction, otherwise do something else. I can only check one at a time. And which is why you have this weird structure out here where first in NS1 I check for LT, then I move to NS2, I check for east-west, and then I spin back. Okay, so I keep, I couldn't, in a single state, I couldn't have simply said, I cannot do a multi-way jump. I cannot say jump to LT1 under some condition or to east-west 1 under some other condition or stay put. I cannot do a three-way branch. Ideally, that's what I would have liked to do out here. I would have said, if left turned but not east-west, go to LT1. If not left turned but east-west, go to EW1. And otherwise, stay put. I would like to do all three in one go, but since the branching approach only lets me specify one branch target, I cannot do that out here, so I need an extra state. The penalty of that extra state is that I have to spend an extra clock cycle. So let's imagine I'm in NS2, east-west is false, but left turn has happened. Left turn light came on. I have to first move to NS1 before I can act upon it. So there is a bit of a delay that is going to happen before I would be able to act upon creating this. So anyway, we're going to pick this up further, but gradually, hopefully you're beginning to see that we have branch instructions and all which begin to look like software a little bit.